So one of the problems that we did last time was a problem where we had to try to find the absolute maximum and minimum over some closed region. And so if you remember what happened here, we focused on trying to find the critical points and then checking the boundaries to see if we have a maximum around the boundaries, and then maximums or minimums around the boundaries. So today we're going to kind of carry on with the same ideas, except we're going to focus mainly on the boundary. Okay. So I guess if we take this example, I'm going to copy it, but I'm also going to change our example here. It's always kind of dangerous when I try to make up my own problems. I hope this goes okay. So let's see about maximizing this function z is equal to x times y squared. But this time, instead of having a domain, a two-dimensional domain, I'm going to restrict ourselves with just the boundary. And for the boundary, I'm just going to choose, this kind. Instead of using the quarter circle where we have to check the lines, let's just say x squared plus y squared is equal to 3, just on the boundary. So the question would be, maximize this function given the constraint x squared plus y squared is equal to 3. So what we're doing is that just being restricted to this circle as your domain, where are we going to find our maximums and minimums? Okay? Can you visualize this? Okay, let's see if we can visualize this. And I'd like to use a 3D plotter, but the graphing calculator is a lot easier for me to control. So basically, I'm interested in this function. And I want to see what happens to that function, but not the whole function, but I just want it restricted to a specific domain. What happens if I type x squared plus y squared? Equals 3. I'm actually going to get a cylinder, so this might be harder to see. Or maybe it's not. So if you look at where these graphs intersect, you can kind of see high points and low points, right? So that's what we're interested in. We're essentially interested in finding those critical values. So one way to do this is for me to parameterize the intersection, and then in that parameterization of the intersection, I can try to find the maximums and minimums. That's like my go-to solution for a lot of these things, is to try to parameterize a curve, 2-dimension or 3-dimensional curve that would help me find the answer that I'm looking for. But it turns out that I think there's going to be another way to try to find this, to find out where they intersect. So let's see. And the way to approach this is to look at their gradients. What do we know about gradients? Vector. Good. What else? This direction of maximum increase. You guys remember all that? Is there anything else you guys remember aside from Brian? Perpendicular to a level curve. All right. I have these two functions here. I'm going to actually change my picture and make it look like, and I want to try to get the gradients involved here. If I want a picture of the gradient involved, how is this picture going to change? Or where would my gradient be? You understand the question? Not of the intersection curve. Let's say this is my function. Z is equal to x squared, or x times y squared. That's my function. If I find the gradient of that, you could probably tell me what the gradient is off the top of your head, but if I find the gradient of that and then graph it somewhere, how's my graph going to look like? Everybody except for Brian. Do you hear what he said? He said XY plane. He said plane. But it's a two-dimensional vector, right? So we're looking at a picture in 3D. If we just focus on that one graph, this is a picture in 3D. And if you were to give me information about the gradient, this is f of xy is equal to x times y squared. And if you tell me what the gradient is, you're going to give me a two-dimensional vector. So if I were to graph the gradient here, the gradient is going to have to be two-dimensional, which means I have to bring this whole picture down to 2 dimensions. And so how am I going to do that? With level curves. Okay? So let's see if I can change the whole structure of this graph and take a look at level curves. So these are my level curves for this graph. Right? Now, this graph over here, let's see if it'll draw. Oh, there it goes. This graph over here can be seen in 2 dimensions as a circle because this is an x and y relation. There's no z in it, so this is a graph in 2 dimensions. Now, I want more level curves here. How can I draw more level curves? I thought I had more control on this. That doesn't help. Oh well, guess I'm going to pretend to draw more level curves. So if I draw more level curves, I'm more interested in the level curves that are closer and closer to this graph. So if I draw more level curves, I'm just guessing, but my level curves are probably going to look like this. Right? So I am concerned, though, about the heights of these functions, specifically on this circle, which I'm calling the constraint. Now, if I take a look at this, I kind of see a couple of possibilities for my minimum and a couple of possibilities for my maximum. Kind of sitting in those spots over there. And I know it's kind of hard to try to visualize this, but where do you think those maximums and minimums would be? It has to be on that circle, right? So the question is, can those maximums and minimums possibly be over here somewhere? Where do you think they would be? I think they would, those maximums and minimums would happen where it would be tangent to those things. So I kind of see 4 2 minimums and 2 maximums over here. So there's these 2 minimums and 2 maximums that are going to go into these things. And the curve looks like it'll be tangent to, the level curves look like they're going to be tangent to each other. What does it mean when curves are tangent to each other? So level curves are tangent. This is that circle. And this is one of those level curves that happens to be tangent. Right? What do you call these again, Lisa? They're called kissing curves. Some people call them kissing. Sorry. She brought that up a while ago. What's interesting about this is that these curves are tangent to each other, and they barely touch like this. And if you were to draw a tangent line to this circle and a tangent line to this other curve, you'd essentially have the same line. All right? But what's more interesting about this is that this vector that I just drew is what? It's the gradient. It's perpendicular to the level curve. And we know that a property of the gradient is perpendicular, that the gradient is perpendicular to a level curve. And then you can also see that the gradient for the other curve is also perpendicular to the tangent. Well, if the tangent is the same, then it's either going the exact opposite or going in the same direction as the other gradient. So if this is our constraint, and we can call our constraint, our constraint is x, y is equal to a constant, right? It's like g of x, y, which in this particular problem, it's x squared plus y squared, and it's equal to a constant. And then our function, we have a level curve for this function. This is the function that we're trying to maximize or minimize. F of x, y. And our problem was, what is it, x, y squared? And this is equal to this particular level, whatever level this is. It's equal to a constant, and then now we have a two-dimensional curve that we're looking at. And so these arrows that I just drew, the blue arrow would be the gradient of g, because that's the constraint. And then the red arrow, whether it be pointing the opposite way or in the same direction, is the gradient of f. So if they're pointing in the same direction or in an opposite direction, what can we say about the gradients? Let's say a bunch of things, but not necessarily, because the absolute value of this, I mean, I purposely drew this red vector a little bit shorter than this blue vector, so the lengths are not necessarily equal. The direction is the same or opposite. What can we say about that? if the direction is the same or opposite. In other words, I want to make an equation with the gradient of f and the gradient of g. They're multiples of each other. And so you write that one is a multiple of the other by saying something is equal to some constant. What should we use for a constant? Let's use lambda. So lambda is a Greek letter L that was named after Lagrange. And this is the lambda multiplier, or the Lagrange multiplier. So grad f is a scalar multiple of grad g, which means that they're collinear, pointing in the same or opposite direction. They're scalar multiples. Okay? So this is the whole theory behind Lagrange multipliers. Or we could take this up to another level where we could take a look at functions of x, y, and z being constrained with the surface. But really, this is the only equation you need to know for Lagrange multipliers. Now, as innocent as that may seem, when you actually start doing the problems, that's when you start getting headaches. Unless you have Wolfram Alpha and you just type in and get the answer. Right? No. It wouldn't. So, what it's going to boil down to is, 3 equations and 3 unknowns. Again, innocent sounding, right? No. But that's really what it is. You'll have a number of equations, a number of unknowns, but trying to solve for that can get really, really tricky. So let's finish this problem up. Again, it's a problem that I made up, so I'm kind of scared to do it. But let's see. Not like the problems that they have are easier. So this is our situation. We want to maximize this function given this constraint. So let me just copy and paste that somewhere else. I lost something. Is that the only thing I lost? All right, maybe a T there, or the T already. So this is my F, and then I'll assign this to be my G. So we're going to have X and Y as the values that we're going to be looking for, and then we're also going to introduce this lambda. So we're going to have 3 unknowns. First, let's find out our gradient. So let's take grad f, which is going to be y squared 2xy. 2-dimensional vector, right? Function of 2 variables. Grad g is 2x and 2y. So if I do my magic Lagrange equation, then I'm going to have y squared comma 2xy equals lambda 2x 2y. And if I take this apart component by component, I will get y squared is equal to lambda times 2x 2xy equals lambda times 2y. Wait, that's only 2 equations. I need I have three unknowns, so I need a third equation. What did you point at? Constraint, the G. So this is always going to come in as your third equation. So x squared plus y squared is equal to 3. So you're going to get as many equations as variables from the lambda relationship, and you're going to be one equation short. You can always find that one equation from your constraint. Okay? So now just go at it. So when you solve for this, you just have to be careful about dividing by variables. When you divide by variables, you kind of eliminate the idea that that's going to be 0, right? Like for the second one over here, there's a 2y that I'd like to get rid of, and then 2y, get rid of the 2y. That means I'm only going to allow that to happen as long as y doesn't equal to 0. And if y was equal to 0, I'll have to set that aside as a special case. So let's try to solve for this, and let me start with that. That's not always the best place to start. But as long as y does not equal to 0, I can do this. X is equal to lambda. And if x is equal to lambda, I can put that back into the first equation. Y squared is equal to 2x squared. And if I know that, I can put that into the third equation. X squared plus y squared, which is 2x squared, is equal to 3. So my x looks like it's going to be positive and negative 1, right? There's a 3x squared divided by 3x squared is equal to 1. So x is equal to plus and minus 1. Now, if I put that into y, then I'll get y is also equal to plus and minus 1. You kind of have to do this carefully. You put x is equal to 1 in there, and when x is equal to 1, you'll get y is equal to plus and minus 1. So you'll have 2 points, and then you put negative 1 in there, and you get y is equal to plus and minus 1 again, so that's another 2 points. So we ended up with 4 points here. Did we figure out what lambda is equal to? Wait. Do we care what lambda is equal to? If you have to find lambda to solve for this, then you'll get lambda. If you didn't get lambda, but you found x and y, then don't worry about it, because I don't care about lambda. Yeah?
Yeah, x is plus or minus 1, and y is plus or minus 1. X squared plus y squared does not equal 3.
Oh, yeah, that's square root of 2. Yeah. Thanks, Pat. What is it again? Square root of 2? There, is that better? All right, so again, I kind of rushed through this, but you have to be careful when you put 1 in there. Like I wasn't careful. When you put 1 in there, you're going to get 2 values. When you put 1 in for x, you're going to get 2 values for y. So when x is equal to positive 1, for example, we got 2 values for y, which is negative root 2 and positive root 2. And then when you put negative 1 in for x, you also got 2 values. And that's negative root 2 and positive root 2. So you ended up with 4 values, which kind of coincides with what we were looking at earlier in the picture, right? The picture we're looking at had 3 of those, had 4 points. And they look fairly symmetric. I just thought they would be exactly equal to each other, but I guess it makes sense that it wasn't. Let's see the level curve again. Yeah, I can't tell, but if you look very closely, the level curves look like they would be coming down closer to here than right in the middle, not off of the diagonal. All right, so we're not quite done yet, but this is like the extreme value theorem. These would be like your critical points. These are the points that are good candidates to be max and mins, and to actually find out whether they are max and mins, you put them back into the function. Which function? The f function, right? xy squared. So we'll take turns putting them in. F of 1 comma negative 2, or negative square root of 2. So negative square root of 2 is being squared. So this becomes positive 2. So this is 2, right? And then f of 1 comma positive 2, since y is being squared, it's going to give us the same value. And if you put negative 1 in there, that's going to be a negative 2. Putting it back into f. So I got a couple of maximums, couple of minimums, again, coinciding with the picture that we got earlier. So that's it. And we can verify and make the picture look nice, and we can verify by just putting those planes. Actually, we can kind of see it right on top. The z value goes from negative 2 to 2, and you kind of see it end right on top there. So I think that's good enough explanation without the picture. So I think the most difficult part is solving for these. Coming up with the equation is easy. Finding the gradient is easy. Setting them equal to each other is easy. But now you have 3 equations, 3 unknowns, and solving for those variables is going to be your biggest challenge. All right, let's. Is that good? Any questions? Should we try another one?
So that y cannot equal 0, that wouldn't be a critical point if we actually ended up with a critical number as y equals 0, right?
Yeah, I kind of set this aside and forgot about it, and we really shouldn't forget about it. So when y doesn't equal to 0, this is what could happen. So we have to account for what happens when y does actually equal to 0. So we should make another case for that. When y equal to 0, we have 0 is equal to 0, the first equation. The second equation will not give us very much information. We'll have 0 is equal to lambda times 2x. When you divide any of these things out or solve for any of these things, it's not going to give us any information. And then we put into the third equation, x squared plus 0 is equal to 3. So it looks like possibility is x is equal to less than minus square root of 3. So then you have to actually consider these pairs as well. Square root of 3, 0, negative square root of 3, 0. And then plug that in, and we'll see that we're not going to get. So negative 3, negative square root of 3, 0 will give us 0, and f of positive square root of 3, 0 will also give us 0. So what happens at those points is they're kind of critical points as well, but they go up here, but they don't surpass the other ones. So it is important that we consider those things that we took out. Does that make sense?
So those are just local max and mins?
Yeah, they're kind of critical points based on the constraint. So based on the constraint. If you look at this constraint, if you look at the intersection between these two things, you got a maximum, it goes down to a minimum, a local maximum, it'll go down to a minimum again, it'll climb up to be the maximum again. So it's like a roller coaster ride up there. So they have a lot of maximums and minimums, and it turns out that 2 of them happen to be absolute max, 2 of them absolute mins, and then 2 others are local max and mins that did not surpass the absolute.
So if there was a peak that went up to 2, it wouldn't matter.
Yeah, if there was something in the middle that went up there higher than any of these, that wouldn't matter because we don't care about what's inside or outside. We only care about the constraint right at the boundary. Yeah.
So would those points not be saddle points then?
No, because we wouldn't. I mean, we would check them differently if they were going to be saddle points. So here we're just looking for absolute max and mins within the constraint. Right.
How do we know that these work?
By looking at this picture?
So without using the picture,
Oh, without using the picture.
we have to use this.
No, all we have to do is plug it into the original function. So this is, yeah, the value that we get out of it. And I totally forgot about it because I was really just looking for those corners, but AJ reminded me of the not letting y equal to 0 means that this is what's going to happen when y does not equal to 0, and I've basically put aside the fact that y could actually be equal to 0. And when y does equal to 0, we have to consider that as well, because they could have been max and mins. So,
When do you consider this condition?
part?
Is not equal to 0?
Oh, because I had to divide by y. That was one of the first moves I did. So whenever you divide by a variable, you always have to put that in the back of your mind. Okay, if I'm going to divide by x, then x can't be equal to 0. For this case, which means I have to go back and consider the case where x does equal to 0. Okay. All right, so I can't put this any lower. But these points over here that we just got, let's do them, I guess, in green. Are these places where along the boundary it hit the local max and the local minimum, but it wasn't the absolute max or minimum. So without the picture, you'll see that they'll pop up as some value. But then you're still looking at the absolute max and mins out of those things. Okay? All right, so let's see if we can do another problem. And we were should we do another 2-dimensional one, or should we just be daring and just jump to 3D? Wow. We got a bunch of problems to choose from. Pick a number between 11. Oh boy. All right. So this is our issue. Now, like I said, the same idea applies, except it's going to be, these are level surfaces. You have to consider a level surface, and then a level, you can look at this as a level surface of some other 4-dimensional function. But still, the gradients are still going to be collinear. So we're still going to come up with the same equation. So the gradient of f is equal to lambda times the gradient. Whoa. Lambda times the gradient of g. So we need the gradient of f as and because this has 3 variables, automatically going to have three components, and then the g, this g is going to be equal to 1. The gradient of g is equal to 4x cubed plus 4y, not plus. So if you do this like once or two or three times, then you'll just figure out the equations without having to write this thing. But I'll write it one more time, and then next time I'll just jump straight into the equations. So we set them equal to each other. Here are our equations. We got 2x is equal to lambda 4x cubed. 2y is equal to lambda 4y cubed. 2z is equal to lambda 4z cubed. And the constraint, which is x to the fourth plus y to the fourth plus z to the fourth is equal to 1. So here are 3 equations and 3 unknowns. 4 equations and 4 unknowns. Okay, so what do? We need to solve for this. We could. So we divide it by 2x, and so we have to consider the fact that this is going to work as long as x is not equal to 0, which means on the separate case we have to deal with the ones where x does equal to 0. So we got 1 is equal to lambda times 2x squared. Now what? Suppose we can do the same for all of them. Let's consider when y does not equal to 0. And when z does not equal to 0. Yeah, so if we kind of do this a little bit trickily, you can just get x by itself. I'm eventually going to want this to be x to the fourth, but if we get it x by itself, we can divide by 1 over 2 lambda, and we'll see that y squared and z squared would be the same. Right? And then we want to square those and put it into here so that now we can get the fourth equation involved. So we'll put 1 over 2 lambda squared plus 1 over 2 lambda squared. So this is x squared, so that's x to the fourth. This is y squared, that's y to the fourth, and then z squared, and this should all equal to 1 according to the constraint. So we got 3 over 4 lambda squared, and then lambda is going to equal to what? So reciprocal is 4/3. Divide become 3/4. So I think it's root 3 over 2. Yeah, I did. Something like that. Is that? Would that work? All right. So now we got lambda. Didn't really care much for lambda, but we got it anyways. And so we're going to, we'll plug this into to find my x. I'm really concerned about my x, y, and z. That's all I really want. So I put this into the x squared, y squared, z squared business.
Once you plug it, it gets to 0,
Or just take square roots.
yes.
Any way you want. So let's take this information, and maybe I should do this in a different color. Take this information and put in lambda is equal to square root of 3 over 2. Oh, I can't put negative values in there because that takes square root. So
Do you have to consider when lambda is negative as well, or do they just get thrown out?
they just get thrown out because it just wouldn't fit here. I hope. So 1 over 2 lambda, which is root 3 over 2, and so that's just a root 3. And so x is equal to the square root of 1 over root 3. That's another way to write that. The fourth root of 3, or 3 to the 1/4 power. So that's your x value. And then similarly for your y and your z values, I think they'll be the same. Or 3 to the negative 1/4. So, we lost the negative lambda because we can't take a square root of a negative number, so that's not going to be part of it. So we just consider positive ones. And then it looks like there's only one point for this case to consider. Now we got to run back and consider the cases where x does equal to 0 and where y does equal to 0 and z does equal to 0. So if x equals 0, the first three equations aren't going to give us any information. So we just have y squared, or y to the 4th plus z to the 4th is equal to 1. And then from here, I suppose we can just, since we don't have any other ways to solve for this, we can just assume what if y is equal to 0 here, and so what's z going to equal to? Can it be negative? I don't know if it can be negative.
Yes.
Yeah, it could be negative. So it looks like we got 2 more points, 0, 0, 1, 0, 0, negative 1. And then if we just play around with the different combinations of which ones are 0 and which ones are non-zero, then we'll probably come up with 4 others.
So we have like all the kind of permutations of this?
Yeah, if it applies. There's some where it's not going to apply, but this one I think it does. So we have 1 point here. What is it? 3 to the negative 1/4 power. Suppose I can. Oh, it's a point. I was going to treat it like a vector, and then your other 6 points The other 6 points look like this. So now the next thing to do is put them into the function to figure out which ones are maximums and minimums. And the function is x squared plus y squared plus z squared. So f of this is going to be 0 plus 1, whether the z is positive or negative. And then f of this next two choices would also be 1. And similarly for this. And then when we put this into the f function, we're going to get we have to square each one, so that's just 1 over root 3. 1 over root 3. 1 over root 3 added to itself. Is it root 3 over 3? 3 over root 3? No. Just root 3? Just root 3. Which is bigger than 1. So it looks like this is a maximum.
And then the other 3 would be minimums.
Yeah?
Or
The other 6. Lagrange, find the maximum and minimum value of these functions. So I suppose, yeah, it would be. I got lost. What happened again? What's the max? Oh, yeah. So if they're looking for the actual points, you would give them the points, but they're actually they were asking for the maximum values and minimum values. So to answer that question, just one. So the minimum values is 1, and the maximum value is root 3. Okay? All right. That was fun. So, should we do another one? One more? What? I was going to draw this. We could draw it, but let's talk about let's draw it first and let's talk about it, because there's something interesting that's going on here. So I'll draw the constraint first. It seems like it would make sense to draw that. X to the 4th plus y to the 4th plus z to the 4th equals 1.
Before you draw it, how do you have 6 minimum values and only 1 max value? Doesn't it have to go up and down if you have minimum values?
Well, that's the thing. That's the thing.
Okay.
You said up and down, right? And then Jesus said, draw it. Okay, I'm drawing it. So, and I was hesitant to draw it. Why was I hesitant to draw it? Because how am I going to graph the function? Make it a level surface, right? So, x squared plus y squared, whoops, plus z squared. Now, in terms of the function, this is my function. This is what I'm trying to maximize. So am I finding the highest height? What's my height? What variable would I usually represent as my height? Z. So z is kind of embedded in here already. So that's not my height. My height is
W.
W. It's a fourth dimension here. Okay? So let me just type 1 in for now. And I see that these surfaces don't seem to intersect here. Oh, what if I... Yeah, one's inside. What if I made this yellow? So to really see a better effect here, oh, too fast. A equals 0.5 till 3. No, it's not growing. Oh, not growing because I needed to put this as A. So your constraint is the yellow thing. And if I move this, at some point, it's going to touch at those points over there. And then if I, those are your minimums. And if I keep going out, wow, I feel like I should have more maximum values. But I got square root of 3 for that.
Oh, we threw out the lambda, you remember? The negative lambda?
Whew. So anyways, to answer your question, and we'll go back to this because I think we did something wrong. Which question am I answering? Oh, AJ's question about the height, the maximum. We're trying to find the height. The maximum is not the height. The maximum is some fourth dimension that we're not seeing. And the only way we're kind of looking at it or trying to visualize it is by seeing what the constraint value is. And so the A value is what we're looking for. Square root of 3 is about what? 1.7. So if I move this A value to be about 1.7.
Oh, it's the last value that stuff is still inside the constraint?
Yeah. So that is going to be the maximum value where the two surfaces are kissing. So the first value where they kiss is supposed to be here. You can kind of see it. It's happening. It's happening. It's happening at the axes, right? 0, 0, 1, 0, 0, negative 1, and all that stuff. It's happening over there. Trust me, they're kissing. And so the other place where they would be kissing would be at square root of 3, which is right here, which means we should have gotten 8 numbers instead of just 1. And I think it's we threw out a bunch of negatives. Well, yeah, that's the thing, is that when we took the square root, you got x squared. When we take the square root of this to get x, it's plus and minus, right?
Let's look from the back of the book, and it says the maximum is root 3 and the minimum is 1.
Yeah, but okay. Yeah, but the points where they happen. Yeah. So the points where they happen is what I was kind of looking for.
So would we possibly assume that it's just the negative for each of the negative 1 point for all of those values?
Yeah. Well, any combination of plus and minus is here. So when we're looking for the x, y, z, when we're looking for the actual points, we need to take the square root, and when we take the square root, and then we throw in the plus and minus business, right? Which I didn't do, so that's what we should have done. Yeah, so right here, plus and minus. Oops. This is the x. When we took the square root, plus and minus, and then plus and minus, plus and minus. So the combinations of pluses and minuses over here would give us the 8 points. But like Aaron said, you know, the book was really just looking for the maximum value and the minimum value, which we got. But what we needed to do is to make sure to see the visual for this. We want to look at the actual points that achieve those maximum and minimum values. AJ.
So for the value, in this case, since we have, like, we're graphing a sphere, we're talking about the radius of the sphere, right? So those values are actually just the radius of the sphere.
Not quite the radius of the sphere, because this x squared plus y squared plus z squared is your f of x, y, z, right? And so whatever that's equal to is the value that the function would output. So I initially was looking at that, and I thought it was the radius of the sphere, but the radius would be the square root of a, not a exactly, right? So I think we could take a look at those two possibilities. When this is equal to 1, and when it's equal to the square root of 3. Let's see if I can get the graphs on our notes and then comment on it to something that makes sense. So 1.73. We'll make it 1.7 because you can see those little things.
So do we ever care what lambda is, or is that just to help us solve our...
Just to help us solve. In this case, we actually had to find lambda, right? We got a value for lambda. But in terms of what we're looking for, that value didn't matter to us. So in this first drawing over here, we have these points 1, 0, 0, 0, 1, 0, and this has a function value of 1. So that's when we found our minimum value. And on the other graph, we have these points in the corners. So this is our point, the fourth root, right? 3 to the negative 1/4, 3 to the negative 1/4, 3 to the negative 1/4. And then you can find all the other combinations of positive and negatives of those points. And this has the f value of square root of 3. And again, that square root of 3 is a value that can't be represented geometrically, left, right, up, down, business. But it's a fourth dimension value that can either represent a temperature or something that's not in geometry. Yeah.
So in Calc 1, optimization was used for a bunch of word problems.
Mm-hmm.
How would we use this in word problem form?
Oh, we just put words to them.
Instead of like, what is the min and max value of
Well, I could say my temperature in my room is x squared plus y squared plus z squared. So that gives me the temperature wherever I am in the room. I'm at 0, 0, 0, my temperature is 0. I'm at 1, 1, 1, my temperature is 3. And then I have a box-looking thing in my room that's described as x to the fourth y plus y to the fourth plus z to the fourth, and there's an ant walking on that box. If that ant can only stay on that box, what is the maximum temperature that that ant can achieve, and what is the minimum temperature that that ant can achieve? And where is that ant going to be able to achieve this maximum and minimum? Or we can just look at an actual word problem. Wrong. So it's like the same idea, right? You got for your Calc 1 stuff, you're trying to maximize a distance given that you have to take a certain path. That's your constraint. So it's the same kind of idea. They have a lot of economics problems here, econ problems. Not a lot, maybe, but I usually look for the Douglas-Cobb. Number 25. So let's, we're not going to do this, but let's just examine the mechanics of it. So total production of a certain product depends on the amount of labor used and the amount K, capital investments. Cobb-Douglas model. P, the production, is equal to this. It follows from certain economic assumptions that A and alpha, or B and alpha, are positive constants. Cost of unit labor. And so, yeah, I don't think we can do this. Trying to maximize the production subject to the constraint that's equal to this. So this is your production. This is like your F function. That's a function of B and alpha. And then your constraint is this. So M alpha P over M plus N. K is 1 minus alpha P over N is equal to P. So this is your constraint. If you try to simplify that, it looks like it'll just be another function of B and alpha, and so you're on in your way to solving for this problem. Aaron? Okay, so that's a general idea. Now there's another step to this where you're trying to maximize a function and you have two constraints. So you're going to have two lambdas, but we're not going to do that. And that would be the same idea, except you're going to be solving for, you're going to need 5 equations instead of the 4 that we've had. Okay? All right, so I think that's enough to chew over. Good luck with your homework. There's a quiz tomorrow. Gradients and directional derivatives.